So let's do an example. There's the tricky part for the Monte Carlo is the hit testing. And there's a couple ways to do this. I will talk through a way that is a very specific solution for a specific problem. In general, what I would say is you should probably use something like a polygon hit test algorithm to test whether or not a ray going through a particular surface actually is contained within that surface. In this example, what we're going to do is just do the geometry of it, and I'll show you how it works. But before we get into it, a hit test algorithm basically says, I'm going to take a ray, emit from a certain point, trace that vector along, and then in space I define the coordinates of some polygon. It doesn't have to be a square, it could be whatever, but it has to be planar. In that planar space, you can then use this algorithm to check whether or not a vector that's going through space actually passes through the internal contained part of that geometry. So those things exist, and it's not something that you need to necessarily recreate. But I would, in general, suggest using that. But we'll go through this just to show you how it works, how the geometry part of it works. OK, so in this case, what we'd be doing is you have these two surfaces. We're going to come down here, and let's emit a ray. First, we're going to pick our position. Let's say that position is here. So we've randomly picked our position on surface 1. And then we're going to emit a vector. Right? So let's say we just emit a vector in this direction. And that vector has an angle with the vertical. Sorry, how's this drawn here? The vertical angle we'll call theta. So I think in the last slide I had it going from horizontal, but either way it doesn't really matter. Vertical angle we'll call theta, and then the let's see, this coordinate here, let's say it's going like this, and that is called phi. So okay, we are picking theta. When we're picking theta, one thing that we have to be careful of is, again, this is the tricky part where you can introduce bias in the results unintentionally. So if you think about like a particular theta from that normal, and you look at the circle that's contained within a given theta, for a given d theta, the circle very near to the vertical ray is going to be a small area. As you get larger and larger theta, the d theta times that circumference is bigger. So the area that's available to emit rays is bigger and bigger as you go to larger theta. So if you want to actually emit uniformly as a function of theta, you have to correct for the fact that there's more area available at larger thetas, right? More area in this dome around the vector. So to correct for that, we would say, okay, my theta is going to be equal to, the theta I pick would be equal to the inverse sine, or arc sine, sine to the -1 of the square root of the probability of theta. So what does that mean? That means I'm going to pick a random number. That random number is between 0 and 1. That's my p theta. I'm going to take the square root of that random number, put it through the inverse sine function, and that gives me my actual theta. Right, so that's how I'm going to sample to correct for that. Generally, that's how you do it. Okay, when we're sampling for phi, that would be just plain old 2 pi times the probability of phi. So my 0 to 1 times my circumference. There's no bias involved there. And then, of course, the x and y would be uniform in those coordinates. So that would be the sampling mechanism there. OK, so then what you need to do is compute like the intersection lengths for this. So you do that by using the vector component. So I'm just going to give you the equation in terms of the angles, which you could just get from geometry. But you'd be saying my radius vector, which we'll call this r here, this radius vector is cosine of phi times sine of theta times the vector component I. plus sine phi sine theta j plus cosine theta k. Okay. So this would be the vector expression of this sampling. Just geometry again. You can figure that out yourself, but sometimes it's good to refer to it. Okay, so this is these are sort of the setup tools you'd need. So let's look at on the next slide how you'd actually do the test for this, how you'd test whether this ray goes through surface 2. Okay, so we have this geometry. We have B1. B1 is the gap between this. We're kind of looking end on now. So it's the gap in space in this coordinate. The actual square is contained within this B2, and then C is the width of this. So if we're going to do the calculation here, what we want to do is figure out the actual length that it would the vector would take from the origin of the emitted ray to the hit in the surface. So let's call that L. But to get to L, we need to write out this vector. Let's see, R. So R is our. Let me just look at my note here. So R is going to be. So R is the vector from the origin on this surface down here up to the hit point. So we would write that just generally as saying, okay, I'm going to start at some x0 position times the I component plus y0 j plus z0 k plus r times L. Okay, so then writing that out further just to see what I mean here, we say this is going to be x0 plus L cosine phi sine theta, that times I, plus y0 plus L sine phi sine theta times j plus z0 plus L cosine theta times k. Okay. So this is just a general expression that helps us get from origin to intersection. What we need, though, is to actually solve for like the coordinates of that intersection. So let's keep in mind that I guess there are specific things about this problem that are true. So that is, first, that y0 plus L sine phi sine sine theta is equal to 0. So that's saying what? That's saying that if I go from my starting y position, confusing myself here. Y, okay, the y coordinate. Oh, I know it. I'm thinking of the, let's look back at this for a second. So I was confusing myself because I switched around the coordinate system. So y is actually this coordinate here. Sorry if that's confusing. So y is this coordinate. So I'm trying to say I want to go from here to here. I know that the intersection up here has to happen at y equals 0. So knowing that that's true, we're saying that my initial starting y plus this distance that the vector is traveling in y, or minus that, has to be 0. Right? That the other way has to be 0. So okay, that's true. What else can we say? We can say that the length of this vector is going to be equal to minus y0 divided by sine phi sine theta. Right, that's just solving that equation right above it. Okay, so then for the x, we're going to say the x intersection point, xi, is going to be x0 plus L cosine phi sine theta. Z intersection is going to be z0 plus L cosine of theta. And then that basically specifies it, right? So what do? We wrote out this general equation. Then we're looking at specific components within that. So like y intersection has to be 0 here. So this equation is where we get L from. And then we also, once we have L, can compute xi and zi. So you can see why this is a very specific solution to this specific problem, because it's just this geometry. If it was a real general ray tracing code, you would not do this. You would use a hit test on the polygon. But anyways, you can see what you're trying to do is work your way back to the intersection based on the ray coordinates and angles and such. So then we're not quite done, right? Go ahead.
So is a hit test like a more general form of this, or is it something else?
It's something else. So it's the one that I like to use is something called a winding number. So it looks at it. You find the intersection in the plane of this emitted ray, and then it's going to compare the coordinates of that intersection in the plane to the coordinates in sort of clockwise order in each dimension. And then you sort of add 1 if it's to the left and subtract 1 if it's to the right. It turns out in the end, if you get to 0, that thing is contained within the polygon, even if it's a non-convex polygon. So it's kind of a cool algorithm. But I think in the homework, I'll maybe give that function to you guys and you can use it. OK, so we've got this information. We know L. OK, what happens if the ray that's emitted goes away from the surface? We would have like a L that's maybe negative or something, right? You'd have to go down in the geometry for it to intersect or something like that. So you have to enforce now with this geometry. You have to enforce conditions that will tell you whether or not it's actually inside the geometry. So those conditions for this particular problem would be hit if first 0 is less than xi is less than c. So if our hit coordinate is in between c, right? It's in this range of c. That is requirement 1. Requirement 2 would be it would be, we want the z coordinate to be between b1, zi, and b1 plus b2. So it's got to be up here. And then the third requirement for this, is L has to be greater than or equal to 0. And that one's a little confusing, but what it's saying is you can go through and solve all this stuff. If the ray is going the wrong way, L is going to be negative, which is nonsensical, right? You can't have a negative ray length. So if L is non-negative, then you end up having a solution here. So you do this procedure for 1,000 rays or 10,000 rays or something until the answer stops changing. And then when it stops changing, given all these criteria, then you're done. Okay. So let's see. Handling complex shapes will be the last thing I think for today. So handling complex shapes. This is I think what we'll try to do for the homework. So what you would do for this is, let's say you have some shape, and that shape, I don't know, it could look like anything. Let's pick it to look like this. So you have some hexagon, and I want to know how much light's being emitted from this to some other surface out in space. So the first thing that you do in terms of just handling the emission from this is, how do you decide? So there's no coordinate system here really where you can say, okay, I've got like this coordinate and that coordinate, and I'm going to randomly sample. This kind of gets back to your question. What you need to do is have a uniform, unbiased sampling across the space for emission. So the way that you'd handle this would be to draw a bounding box that covers all coordinates. A bounding box like this that covers all coordinates. You have to excuse my overdrawn lines. But this bounding box is contained within the coordinate system. So this coordinate here is, let's call x. This coordinate here, let's call y. So what I would do is, and again, this could be like oriented in any way, but you just need to make sure you cover the entire shape, would be now I'm going to do a random sampling of the origination coordinate for this problem. So my first random sample is going to be here. Great. That is within the geometry. So then I would emit the ray from that position. My second random sample happens to be up here. That's not within the geometry, so I would not emit. I just say, skip this position, go to the next, right? Eventually, you're going to have a bunch of positions in here that count, and a bunch of them out here that don't count. And then when it comes to evaluating the view factor, you're going to say, let's say this is f from I to j, where this is surface I. Fi to j is just going to be the number of hits on j divided by the number of rays emitted inside the geometry of I. Okay, and the key point, though, is you have to have some way of evaluating reliably that these positions are within the geometry. So again, what we could do is on the emitting surface have a hit test. Like use your polygon hit test. You plug in a coordinate, say, does this go through my originating surface geometry? If yes, then include it in that count. If not, don't include it. So you'd essentially end up having to do 2 polygon hit tests, one for the originating surface, one for the absorbing surface.